we're going to start now. So welcome to Subverting Windows 2003 Service Pack 1 Kernel Integrity Protection. I'm Ionescu, and I'm a developer for Tiny Kernel. So basic roadmap of what I'll be talking about. First, introduction to the actual exploit or the bug. Then a very short introduction to Windows NT Basics. I know probably some of you are not familiar with all the terms I'll be using, so it's just a very simple introduction to the terms I'll be using and what they mean. Then I'm going to talk about some old and deprecated methods which were used to basically access physical memory and edit the kernel from user mode, which is what I'll be talking about, and new methods, both for typical developers that need to actually read physical memory, and also methods that rootkits or specialized system software would use. And then I'll be talking about subverting the actual protection that was added, which I'll explain, and how to actually bypass what Microsoft added to secure the kernel, and what can be done with this exploit, and finally how to protect against it. So simply put, this bug and exploit allows you to do ring 0 access from ring 3. Now, if you don't know what ring 0 ring 3 is, I'll get to it very soon. Because previous methods of doing this transfer don't work anymore in Windows 2003 Service Pack 1. So I discovered a new bug in the NT kernel, which has actually been there for since a long time, but nobody ever found it. This bug requires administrator access, so it's not a security flaw per se, it's an architectural flaw. It allows a program that runs in administrator mode to get access to the kernel, which can still be problematic, but it's not a big security flaw. So the goals of my talk are basically two of them. First of all, to notify attendees about the loss of functionality in 2003 Service Pack 1 due to this protection. If there are any developers here that used to access physical memory from user mode, there are new APIs to do this which are added because the old method doesn't work anymore. And for security researchers, if you're aware of rootkits that use this method, well, you don't have to worry about them doing this anymore because the kernel is protected against it. However, there's a new exploit. So again, for developers, if you really need physical memory access from user mode, this is one way of doing it. I don't recommend it, but if you want to test it out. And for security researchers, again, watch out for any malware that might do this now and how to protect against it. Basically, what this exploit lets you do, it lets you access physical memory for direct hardware access. So firmware updates, BIOS, video, RAM analysis can be done from user mode. It also lets you read-write system variables from user mode again. If you want to provide some deep, low-level system information application, like some information that's not exported to user mode, you could use physical memory for this. And finally, it lets you run code at ring 0, which can be problematic without using a driver. So a lot of people, when they heard about this, and usually when they hear about getting ring 3 code to go in ring 0 mode, they say, you can already load a driver to do this, so what's the problem? Problem is user mode malware that's actually doing kernel mode operations in user mode is much more insidious, and it's hard to defend against because they're not loading a driver. If you enumerate a driver list, if you try to find it on disk, there won't be any driver. And a lot of IDS software, intrusion detection systems, they can actually detect a driver being loaded. But in this case, if the rootkit uses physical memory directly, no driver is being loaded. And also on 64 Vista, there's driver signing, so developers can't just load a driver anymore if they don't pay some money to a company to sign their driver. And finally, it's a lot harder to write driver code than user mode code, so it's again another advantage that not many people could use. So some CPU basics, so we're talking about rings a lot, so just to make sure everyone knows, the x86 CPU, NPMs and all that, they have four ring levels, also called code privilege levels, that go from 0 to 3. And 0 is the most privileged, and 3 is the least privileged. And ring 3 basically blocks some CPU operations, which could be dangerous to your hardware, direct access to your hardware, and registers inside the CPU which control the temperature and things like that, really damage the computer. Those are blocked, and ring 3 is usually called user mode in Linux and Windows and Mac OS. Then you have ring 0, in which you can do anything you want, and that's basically what we call kernel mode. Just like on an operating system that protects files from Joe and Mary, they're separate, and the administrator files are separate, the CPU also uses the same, uses these rings to protect against a supervisor and a normal user mode account. Because the OS would have no way of knowing if your program is actually doing a really dangerous operation that can damage your hardware. It couldn't really stop that unless it parses your file every time you execute it. So the CPU does that. So there's a lot of OS level bugs which do this thing called getting to ring 0 from ring 3 and actually controlling the execution code and having your code running in ring 0. This is a huge problem if you can do it from a non-privileged account, because when you're in kernel mode, there are no user accounts. If you get to kernel mode, even if you're in a guest account, you have more than administrator access. You're gone. So on Windows PCs before Vista, that's a problem because pretty much every home user logs in an administrator account at home. So if they download malware, that malware will execute in administration mode. And normally, it could format your disks or steal data, but it's not supposed to be able to damage your hardware because it's not running in kernel mode. So with bugs like this, you can get a rootkit that actually damages your video card permanently. So some really simple NT basics about Windows NT and Windows 2003. It's a hybrid kernel design, monolithic kernel which can actually load drivers. It uses 2 of the ring levels, 0 and 3, for kernel user mode. And it's an object-based design, so every process, file, thread, they're actually objects which can be accessed only through handles from user mode. And all the security that's handled is built in the kernel, so it's not a special driver, it's not done in user mode, it's done the kernel for security reasons. So like I said, processes, threads, files, events, semaphores, mutexes, and a bunch of other OS level things, in NT, they're all objects, and they're managed by this thing called the object manager, and the actual module that's responsible for what the object represents. So, just like on C++, you dereference an object, you re-reference it, and the actual object manager is going to handle, for example, cleaning up the memory after you're done using the process, not the actual process manager. The objects themselves, they're just in kernel memory, and user mode, all it has is a handle. And this handle is an index into a handle table, which maps every handle to a pointer. And that's also done in user mode, in kernel mode. Additionally, all objects have security information, which is stored in something called a security descriptor. And the object manager is going to talk to the security reference monitor and validate security. So access to objects is done by 2 methods. One of them is handle validation. So process A can create an object like a file with read access, and that gives it a handle, and that handle is for read access. So if he tries to write a file, the NT is going to tell him, this file is open for read access, you need to open it for write access. It's also done by user validation. I can create a file and say, the administrator has write access, but Joe and Mary only have read access. And the actual security is done with a method model called DAC, Discretionary Access Control, using things called ACLs, which are access control lists. So each object has a security descriptor which has an ACL, and that ACL determines access. The way it works is that the ACL has ACEs, access control entries, and each entry describes the access that a user can request, like administrator, read access, Joe and Mary, write access, or vice versa. And there are APIs for actually editing these things. Apart from access levels and ACLs, NT also has privileges and tokens. Tokens basically, they describe a lot of things, but one of them are the privileges that a user has and which ones are enabled or disabled. And even tokens are objects, and they can be edited, and they have handles too. Privileges, what they do is that some APIs are dangerous, so they only work with a certain privilege enabled, and that privilege could be only available for administrators. For example, if you want to create an object that's permanent, so even if you dereference it, it still stays in memory, that could be dangerous because you could constantly create permanent objects and make the computer run out of memory. So to do a permanent object, you need a special privilege, and that privilege is only there for administrators. And that's the information that's stored in a token. And each process in each thread has a token that describes the whole security context and the user. Tokens are really cool because they can be duplicated, impersonated, inherited, and reassigned. So you can launch a program under a guest account, but if it suddenly needs to do something that only the administrator can do, it could, if it's allowed, duplicate the system token, the system processes token, which is the highest privilege, and assign it to itself. So now even though the program was run by a guest account, it now has the administrator token. Or you can even just impersonate the token and give it to some API. Of course, this requires it to be allowed. You can't just do it just like that. So now some methods that we usually use to go from ring 3 to ring 0. On the x86 architecture, you have two typical methods of going from, legally going from ring 3 to ring 0. Call gates for interrupts. Usually interrupts, they jump to something in kernel mode that handles them. And there's nothing stopping you from creating an interrupt that actually goes in user mode in your own controlled code. But call gates and interrupts are in tables called the IDT and EGT. And these tables are only in kernel memory, so normally you can't create your own interrupt. However, on Windows NT, just like on Linux, there's this memory section called /device/physical memory, which is run like /dev/mem, which allows user mode to access physical memory. This is going to be a problem if you want to edit the IDT or the UDT, for example, is because most OSs, they use a structure in virtual memory, which is a way of mapping physical memory using a different mapping, so most processes can share memory pointers. So even if you have access to physical memory, your pointers and your data don't map one-to-one. The CPU usually does this mapping for you. You could do it manually, but that requires you to read a special table which has the mapping, and the table again is in kernel mode. So you're not supposed to have a way to translate between the two from user mode. However, on Windows NT, because of the side effect of the Windows NT Memory Manager and the way it allocates virtual memory when you start it up, for most kernel memory you can use a formula, because it's a simple mask, where the physical address that you need is just the virtual address with that mask. And that mask actually just removes the two top bytes. So if your virtual address is 0x80 ABCDEF, the physical version of that is just ABCDEF. Now that only works for some kernel pages, but it happens that it works very well on the page where the actual kernel is. So the generic methods that malware and low-level software usually use is they use the physical memory object to edit the tables that contain interrupts and call gates. They add their own interrupt, and then they call it, and that code now runs in a kernel without a driver. Some use it to edit kernel structures. Rootkits are going to edit the process list, remove themselves from the process list, so then when you open Task Manager, the rootkit won't be showing up. Other things they can do is to edit the code inside kernel APIs, to bypass security, to change the name of the files that are returned. So rootkit again can hide which files the user can see. Of course, there's also a legitimate use for accessing physical memory. If you want to read the BIOS, if you want to read the CPI tables, a lot of hardware information is available in physical memory and public addresses. So a lot of Windows software used to use this. When some exploits came out to use device physical memory, Microsoft didn't respond to it or anything because, for a valid reason, like I said, this can only be used by administrators. So they said a lot of big security ideas that if you're an administrator, you are root, you are God. So there shouldn't be anything stopping you from actually bypassing ring privilege level. And in XP, they actually added an API which made things even easier called ZW System Debug Control. So this new API in Windows XP allowed direct access to kernel memory through the virtual address. So no more physical memory, no more having to map pages. So it even allowed sending interrupts, talking to hardware, reading and writing highly critical CPU registers. It was originally developed for a feature in XP which is called live kernel debugging, which is a really cool thing in Windows XP. And you can actually debug the kernel live. You don't actually need two computers anymore. But of course, within a few months, people start realizing, well, I can use this in my malware and read through private kernel data and lie to the OS and tell him, hey, I'm a debugger. So again, this also needed administrator access because it had a special privilege. So Microsoft at first didn't consider it a threat because administrators should do whatever they want to do. Of course, Windows 2000 ships, these features are still there, and when SP1 is being developed, the XP Service Pack 2 is also being done at the same time, and they had heavy emphasis on security. And Microsoft actually removed both these threats in Service Pack 1, so you couldn't use device physical memory anymore, and the API didn't work anymore either. And this was not a silent removal. Microsoft, in their marketing and their tech documents, they actually specifically say this change was made to help prevent security exploits that might leverage the functionality of the device physical memory object from user mode. So, from my perspective, I think this was an interesting change in mentality because rootkits became so popular, and Windows phone users, they're all administrators. So, the idea is that you run a rootkit and it hides in kernel mode, so typical security software can't find it. Of course, in Vista, that won't be a problem anymore because users aren't admins anymore. Microsoft knew that removing access to the physical memory object would cause compatibility problems with legitimate software that, like I said, needed to access versus various hardware data. So they added 2 new APIs, which, if you're a developer that's working on physical memory, you should look these up on MSDN. Adding system firmware tables, which gives you a list of which physical memory will let you read, and get system firmware table, which actually lets you read data. However, it's only for reading, you still can't write to it, and it only has some hard-coded addresses. So if you have exotic hardware that you would test or talk to in user mode without a driver, just by using the physical memory object, you need to write a driver now. You can't do it from user mode anymore. So a lot of people said, this will be the end of user mode rootkits with doing zero access, unless someone finds something new. So I did find something new, a new way that bypasses these detections. The keystone, cornerstone of this is VDM, which is the virtual device machine, which is a built-in virtualizer in Windows NT that's responsible for DOS support. And it's based on some 1980 software called SoftPC that I think Microsoft acquired. So VDM processes, because DOS programs access video memory directly, they need video RAM access and they need access to the device for write and read. So and this memory is in physical memory, so the kernel has to map it for every VDM process. So the kernel needs to know which addresses should I map, because every PC BIOS has a slightly different range of addresses where it could be located. So the kernel actually needs to read a registry key, and this registry key contains data of every BIOS ROMs in the CPU, in the computer. It's a very simple structure that has the base address and the size of the memory range. So an exploit seems simple here. You could just edit the key and tell it, hey, I have a ROM located at this address, but this address is actually something in the kernel. But reality is very complex. First of all, the designers who made VDM had some idea of the risk. So any address below 0xC000 is skipped. Because these are usually very important kernel structures like k-user shared data, the kpcr, the page table directory, all these really low-level things. So you can't get to those, but you can get to memory about that, and that's where the kernel code is actually located. And for that, you can use a mask I showed earlier to find out which virtual address corresponds to which physical address. So of course, even how to do this, the problem is you're not a VDM process, you're just an own process. So how do you become a VDM process to be actually able to get mapping done in you? There's an API called NT-VDM control, and you give it parameter VDM initialize. It turns out this one fails because you can only call this from a VDM process. It's kind of like a chicken and egg problem. It turns out that first of all, you need to tell the kernel on the VDM process, and then you can initialize. So if you tell the kernel your VDM, you use NT-set information process. But this also fails because this can only be called by a process which has the subsystem privilege or TCP privilege. And this privilege is only available to the local system accounts. So even as an administrator, if you try to acquire it, you won't be able to. So the idea is, okay, like I said earlier, you can duplicate tokens. So I tried to duplicate the system token and open it for duplicate access. It also fails because the system process does not allow you by default to edit or to duplicate its token. So what you have to do first is to open a token for editing mode and then edit the apples. So the general plan of attack is you open the system process token for apple edit access. This works. Then you edit the apple to give to Adam the ace for the administrator account. That gives it the token duplicate access it needs. You save the security descriptor, you reopen the token with duplicate access, and then you call anti-duplicate token. So now you have your duplicate token, and you impersonate the current thread as a local system thread. Now you're going to acquire the set primary token privilege, which you need to make your process go beyond administrator and become a local system process. Acquire this, you duplicate a token to get a primary token. And you call this the anti-set information process to set this token as your primary token. And now you can acquire the TCP privilege and call anti-VDM control again to initialize yourself. And that also fails. The reason it failed is because the function throws parameters, and all along I was passing no pointer because I had no idea what it actually needs to do to initialize it properly. So I had to reverse anti-VDM, which is the user mode part of the virtualizer. And I looked which structures does it send to the kernel, and I basically cloned them and called anti-VDM control with the same parameters, and that also failed. The reason it failed, again, because VDM wants the memory at 0x0 to be already allocated so it can copy some data. Now this is a problem because 0x0 is mostly known as a null pointer. It's something that shouldn't be allocated, and when you call the allocation API for it, it thinks a null pointer means something else. So the way to allocate 0x0 is actually to send it 0x1. And this way the allocation function knows, okay, he actually wants to allocate the memory at 0x0. So once you allocate it, the API will now finally usually work, but it could still fail because when it actually tries to allocate that memory which you edited in the registry, it might already be used in your process. So you got to make sure that you don't use any of the DLLs which might be using up that memory. So the trick I use is, as soon as I load, I allocate the memory that I know I'll be needing, and I keep it allocated until I finally call the API that I actually used by default. So if that worked, I tried with the default raw messages on my computer, and they were allocated and mapped. So now that I know how to allocate to initialize the VDM process, I can exploit the flaw. So what you need to do is first you calculate the physical pointer for the virtual location of the code you want to modify, and you add this entry in your registry. Then you allocate the pointer 0x0 for a range of 10,000. And then you do token count foo to get that BCD privilege that you need to initialize. You free the pointer. Then you free the memory allocated at the beginning, call into VDM control. Now you have access to that kernel memory. And you'll try to write your patch, probably try memcopy, then ends up failing. Because even if you allocated memory, it turns out you can't write to it. At least it seems that way. The reason you can't write to that memory that just got mapped is because it got mapped in kernel mode with kernel mode flags. So the CPU is when the CPU sees you trying to use it from user mode, it's going to say he's not supposed to do this, and it'll just ignore your writes. However, we have another trick you can use. It's an API called anti-write virtual memory. And this is basically a slow way of writing to virtual memory. But because it's a system call, it lives in the kernel. So the CPU thinks, hey, the kernel's writing now, so I'll let him do this. So instead of a memcopy, you have to use this API, and Ryan can actually write to that location inside your process. That change will automatically go to whatever kernel mode code is there. So now if you can actually patch kernel mode code, what can you do with this? So I thought the best solution was to restore the lost functionality in service pack 1. So because once device physical memory access is restored, you don't need to use this complicated hack anymore. You're basically back to where you were before Service Pack 1. So we move on to part 2, analyzing how does Service Pack 1 actually block access to this object? How do they make it protected? So if you look at the Microsoft documentation for Service Pack 1, they say that even administrators can't open the object anymore. They have protection specifically for user mode access in general. So when I look at the Apple of the object, it matched the one in previous versions of NT. So it wasn't the typical security that was blocking me from getting the object. So this makes sense that they're either using a special flag for this object, or that there's a string comparison done in the kernel, which would be stupid because you can create a symbolic link and that would bypass it. So I thought probably they're using a flag. So I looked at the kernel function, which is responsible to boot up to actually create this object, and I looked at what flags it gives for attributes. Now, these flags are documented, and the highest one that's documented is 0x400. But this function was actually giving it 0x10,000. So this flag I had never seen before Service Pack 1, so I thought, this is probably the flag that they're sending. So I wrote a test driver, I created an object using this flag, and there you go, when I tried to access the object from user mode, it didn't work anymore. So probably the kernel check was being done for this flag. So I tried to look where this flag actually is located in memory. All objects have basically meta structure, which is internally used by the object manager. That's where it stores, for example, the number of handles or the number of references to the object. And one of them is object header, the other one's called object header name information. So I dumped these structures in memory, but none of them had that magic value. So I'm still wondering, where do they actually store the value? The quickest way to find where this flag was being converted or written to somehow was to actually trace the execution for failed open and put a breakpoint and a trace filter that said break when EAX's the return value static access denied. So I let the trace run, and it stopped at the point where the kernel was returning this value. And quickly enough, I decided to check for a much bigger flag, 0x4,000,000, in an object header structure. But only the call came from user mode, so I thought maybe this is what it's checking for. Turns out that we're checking for this value is in the object header name information's security references member, which existed even since 2000, and doesn't really have anything to do with protecting from user mode. So it seems like an obfuscation technique instead of making a visible flag called protect from user mode. So I experimented again. I took the device's physical memory object, and I manually removed the flag from memory, and I tried to open it again, and it worked. And likewise, I tried making an object and manually writing this flag to it, and it became protected. So, in case you're wondering, the feature is not exploitable. Kernel mode only allows you to set this flag for kernel mode objects. You can't have a process that creates, because if it lets you do it from user mode, you could create a process that no one can kill. And but another neat thing is that driver developers can actually use this flag for themselves if they don't want the user mode to start touching their driver for some reason. So with the VDM bug before, you have two possibilities to actually bypass the protection. You can either get the object's pointer and remove the flag, or you can edit the object manager code and remove the check itself. Because there isn't any way of getting the object's pointer from user mode, and it'll always change, that's a pretty hard method of doing it. The easier method is, of course, to patch the kernel at runtime using the VDM trick. If you want to find the code, you can either hard code it like shellcode does, or you can write a semi-complex regex matching routine which finds where this check is being done. So the check is usually very simple to patch. It's usually either GNZ that you need to write from docs, so basically it won't make a jump to failure case anymore, or sometimes replacing a failure case with a jump to success case. So because we have a way to map the kernel user mode, you can just search for the code you need and then use the exploit to change that 1 byte, and now you're back to Service Pack 1 days because the kernel is not actually doing this check anymore. And you can do this live on a system. The user won't have to reboot. So if malware does this, they're not editing anything on disk, they do it in memory, and they bypass everything that Microsoft worked hard to do. Now that you have the device physical memory back, You can even use it to reactivate ZW system debug control, which was disabled in Service Pack 1 as well. And they added a new kernel API. And now what the debugger does is that it comes to the driver, and that driver calls the API. All you have to do is patch the user mode accessible function to actually call the kernel mode 1, and then you get the API back. And now you've totally broken the security and you're back to your own functionality. How to protect against this? Well, don't let your non-trusted users run as administrator, because this only works in an administrator. On the other hand, if you absolutely must, or if you're trying to protect home users from themselves, you can use something in Windows called the registry notification APIs, and they tell you when someone edits the registry. So you can tell Windows, watch this key, the one that I mentioned at the beginning, because nobody's supposed to write to it except the kernel on startup. So if you detect someone writing for the key, then you can just crash the system or crash the application or just deny and pop up a message. And also Microsoft, I notified Microsoft of a flaw, so it's very possible they release a fix, and for Vista we may be backported. A lot of stuff I said now was very generic because I didn't want to go very technical, but I did write a very technical paper, detailed paper with some actually assembly analysis, so everything source code that you can access. It's not online yet, but it will be this week. I'm going to upload it. This is the web address. I'm going to leave the slide on if you want to write it down. The paper also contains sample code which matches the internal proof of concept I used. And finally, as a greed, I'd like to thank William and Jason who helped with the whole concept. And thanks to the audience for listening. And now, if you have any questions, I think there's time to take them. Yeah. And or after talk or by email, as long as you don't ask me how to write malware. So thanks for listening. Yes.
How do you think they got fixed? Because they'll put restrictions on the EVM thing, so it can't have edges or something they're going to do.
As a protection?
Yeah.
Well, a very simple thing you could do is basically the BIOS ROM addresses. They should never go past 0x100,000. There's pretty much limited range of addresses, so it shouldn't let you request any address you want. So that's the simplest thing they could do. Any other questions? Yes?
So you said you could access kernel page frames with this method. Can you also access the user page frames?
Well, the user page frames, I mean, you're already in user mode, so.
Right. But if you wanted to get the physical pages themselves.
Yes, yeah. Not with that mask, but once you use that mask to get to kernel mode, then you can access the page table directory, and that'll give you access to any page frame you want.
Would allow you to access other
Right, you'll get access to other processes, yes. Any other questions? All right, thanks.